Section 3-1, Numeration Systems. We'll start by looking at numbers, where they came from, and how they were represented differently all across the globe. We'll talk about our numeration system, the one that we know and love so well. And then we're also going to talk about numbers that follow the same format as our numeration system, but use different bases. The numeration system that we use, the system that we use to represent numbers, it's actually called the Hindu-Arabic numeration system, and it's made up of digits and place values. We only have 10 digits. They're the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And how we arrange those digits changes the value of the number that we're trying to represent. I've got a little chart here of our place value. We can see in red, I have the ones period. The ones period is made up of ones, tens, and hundreds. In yellow, I have the thousands period. The thousands period is made up of thousands, 10,000s, 100,000s. In green, we have the millions period. And probably a lot of us are familiar with the place values 1, 10, 100,000, 10,000, 100,000, but maybe we didn't know that they're broken down into groups called periods. And when we write numbers and we use commas to separate every 3 digits, what we're trying to do is separate the periods. It also helps us to say these numbers in words if we know what the period is. For example, I can pick any digits I want and place them into these boxes. So let's do some random numbers here. If I wanted to say this number that I've written out, which is the digits 2, 1, 0, 7, 5, 0, 1, 0, 3, I wouldn't just read those digits off like that. When we write that number in words, we start by looking at each period and saying the number within those 3 spaces as if it were in the ones period. For example, looking at the millions, that's the numbers in the green boxes, I would read this as 210. I wouldn't necessarily read it as 200 million, 10 million, 0 million. I would read it as 210. Then I would follow that with the name of the period. So I would say 210 million. Then I would move on to the next period. 7 in the 100,000s, 5 in the 10,000, 0 in the 1,000. I would read this as 750 thousands. So you read the 3 digits within the period as if it were a plain 3-digit number, and then you follow that by the name of the period. So 210,750,103. Now notice I did not insert the word and right here. And a lot of people do, 103. That's actually incorrect. We save and to represent the decimal, which is where you switch from whole numbers to parts of numbers. So we're not going to use the word and anywhere when we're writing out these huge numbers. So I'll read it again, 210,750,103. No and at all. And I could use these exact same digits but scramble them up and it would completely change the value of the number. Let's try another one. Here I've used a lot of zeros, which can really complicate how we think we should say a number. Remember that we're going to follow the same convention. Start in the millions period. Read that as if it's a 3-digit number. It's not 1, it's 100, and then the name of the period, million. 100 million, we have 0 thousands. Nowhere in the thousands do we have a digit other than 0. And then we have 753 in the ones period. So we would read this as 1,753,000. And when we convert this number into words like that, it's easy for us to overlook the fact that I have 5 zeros in here. So we have to be really careful, read it slow so that you can make sure that you're keeping the value of the number that you're representing. All right. Our Hindu-Arabic numeration system creates numerals using digits and numbers, place values, sorry. When you hear digits, you're only allowed to think of these numbers in our numeration system. So, for example, 11 is not a digit. 11 is a numeral, and it's using the digit 1. Whoa. Another numeration system is the tally numeration system. And maybe we've used this before. You just use a tally mark to represent how much of something you have. This is great for representing quantities of whole numbers, right? We don't really have tallies for fractions. We could try and come up with something, but in general, tallies are just counting how many things we have. Notice that there's no 0. We don't have a tally that represents 0. And something that's really annoying about the tally numeration system is if I wanted to represent the number 999, I would have to draw 999 individual tallies. There's not a shortcut to represent large numbers, so the tally numeration system is really cumbersome when it comes to large numbers. There's the Egyptian numeration system, and the Egyptian numeration system uses images instead of digits. So like how we use 0, 1, 2, 3, for example, the Egyptian numeration system uses these images that I have in the table here. We have the vertical staff, heel bone, a scroll, a lotus flower, a pointing finger, a pollywog, or some people call it a burbot, and then the astonished man. Each one of these Egyptian numerals can be converted to a number that we use in our system, the Hindu-Arabic equivalent. So a vertical staff, to us we would just say that's 1. Or the astonished man, to us we would just say 1,000,000. Now, of course, Egyptians need to represent numbers that are not these perfect multiples of 10. So what they would do is use multiple of each numeral and combine them together to represent a larger number. For example, down at the bottom of the screen, I have a number which is in the Egyptian numeration system. And the symbols look a little bit different than what we have in the table, but we can tell that the first 2 are astonished man, which means I have 2 things that represent 1,000,000. So the 2 astonished men represent 2,000,000. Then we see that we have 3 polywogs. Polywogs represent 100,000. So we have 300,000. Then we can see that there are 4 pointing fingers. Pointing fingers represent 10,000. If we have 4 of the 10,000 numerals, that's the same thing as saying 40,000. Then we have 5 of the lotus flowers, which represent 1,000 each. So that would look like 5,000. I see one scroll, which is 100, two heel bones, which there's two tens, so that would look like 20. And then we have two vertical staffs, so that would be like two ones. So the same number in our system would look like 2,345,122. Now, the Egyptian numeration system does a fine job, but our number system represents the same number more concise. It does require us to understand quite a bit more mathematically to be able to use this really concise numeration system. But at least we don't have to draw little men and polywogs and fingers and flowers and all of these other symbols. So maybe we think it's worth it. Now that we've done an example where we take an Egyptian number and turn it into a Hindu-Arabic number, let's do the opposite. Let's take a number that's already in our numeral system, and let's rewrite it as an Egyptian numeration system. So I have a 9 in the ones place, which means I need 9 vertical staffs. I have a 5 in the tens place. 10 in Egyptian is a heel bone, so I need 5 heel bones. I have an 8 in the hundreds place. 100 in Egyptian is a scroll, so I need 8 scrolls. I have a 3 in the thousands place. 1,000 is a lotus flower. I'm going to do a really great job drawing these lotus flowers. Looks just like the picture. Well done. I have a 5 in the 10,000s place, which means I have 5 pointing fingers. We can already feel the pain of trying to draw all of these, just even if you aren't trying this on your own. Very thankful that we switched to the other numeration system. And then lastly, we have 2 in the 100,000s. Those are 2 polywogs. Our polywogs are going to be smiling. There we go. So the number that we would say as 253,859, the Egyptians would draw this picture. So hopefully that makes us appreciate our system a little better. The Babylonian numeration system is a little similar to ours in the sense that it does have a place value built into it. Babylonians used 2 symbols. They used this upside down triangle to represent a single item, and then they used this sideways open triangle to represent groups of 10. And depending on where you put these numerals, it would change the value of the number that you're talking about. For example, we have a Babylonian number drawn out here for us, and we're going to look at the groupings and notice that that's representing a place value. We're familiar with our place values, but the Babylonians did not use that same system. They used something that's a base 60 system, which means, unlike ours, they increase by groups of 60. We use something called base 10. In base 10, our place values are powers of 10. So in the ones place, that's like 10 to the 0. And then in the tens place, that's like 10 to the first power. Hundreds place is like 10 squared. Thousands is like 10 cubed. And it keeps going. So base 10 means that once you create a group that has 10 items in it, you need to move up to the next place value. Base 60 is very similar. The only difference is we're looking at powers of 60 rather than powers of 10. So in their units place, they have 60 to the 0. In their groups, their first grouping, that would be like 60 to the first power. The next grouping would be like 60 squared. The next grouping would be like 60 cubed. And then it keeps going up and up and up. So a number written in base 60 is not going to look or have the same value as base 10, even if it does look similar. And that's because the position of each digit or numeral is representing a different value right out of the gate. So what we're going to do is take this Babylonian numeral and convert it into a number that's equivalent in our numeration system, the Hindu Arabic system. So the first thing we need to do this conversion is to look at the natural breaks in these images where the numbers are so that we can see exactly what place values we're looking at. So I can see a break right here. So I know that this would be like the 60 to the 0 power place value. And then I see another break right here. So between those bars, that would be like 60 to the first. Now, but these next two, it is kind of tricky. Are they separate or are they the same? I'm going to say they're the same. So this would be like 60 squared, and then our last grouping would be like 60 cubed. So let's map that out. So I've drawn out the expanded form for a number in base 60. Notice that I have each of the place values. My ones singles place, that's 60 to the 0 power. And if you remember, anything raised to the 0 power is just 1. So 60 to the 0 power is just 1. 60 to the first power, that's just 60. We don't really need the exponent there. Then we have 60 squared and 60 cubed, and we will worry about what those equal later. Next thing we need to do is translate the images in the Babylonian numeral system into a numeral in the Hindu Arabic system. So looking at the image that's drawn in the units place, we have 4 of those little triangles, which means we're looking at what we would call 4 in our system. The next grouping has just 1 of those upside down triangles, so we would have a 1 placed in the 60 position. And then in the 60 squared group, here's where we see more going on. I can count that there are 7 upside down triangles. I can also count that there are 4 of the sideways open triangles, which would represent 10, a total of 4 times. So really that looks like 40 and 7 in our system, or 47. Now 47 for us is made up with 2 separate digits. But in the Babylonian system, they're not using digits. So they're representing a quantity within that place value the same way we would pick a single digit to plug into a place value. But here we have to use a double digit because 60 is what we need to become a new group. We'll get into that more later. Next we have the 60 cubed place value, which has 4 triangles, so I would put a 4 here. And then if we wanted to convert this into our numeration system, which is what we do, we would type this into our calculator very carefully. I'm going to work it out step by step, but if you want to, you can type all of this directly in on your calculator, starting with 4 times 60 cubed, then add to that 47 times 60 squared, add to that 1 times 60, add to that 4 times 1. So you can type this all in directly, but I'm going to show you how it would work out step by step. First, I'm going to multiply the place values so that we can get a better understanding of what they equal. So 60 cubed is actually 216,000. And 60 squared is actually 3,600. So when we're writing 4 times 60 cubed, we're really writing 4 times 216,000. And when we write 47 times 60 squared, we're really writing 47 times 3,600. And then we have 1 times 60, and then we have 4 times 1. And then if I multiply each one of these separately, 4 times 216,000 comes out to 864,000. 47 times 3,600 comes out to be 169,200. 1 times 60 is just 60, and 4 times 1 is just 4. And now we can add all of these numbers together. And something that you'll notice working within a place value system is that each of the place values allows us to stack our numbers in such a way that there are a bunch of zeros lining up. Oops. We'll line up all the zeros. So I've got zeros with a 4, zeros with a 6, 0 with a 2, 9 and 4 is 13, I'll carry my 1, 6 and 6 is 12, plus 1, 13, carry the 1, and 10. The number that is represented here in Babylonian is equivalent to a number that we would say 1,033,264. Now converting from Babylonian to Hindu Arabic, it's a little bit weird, and we're not going to do a whole lot of this semester. What we will do, though, is convert between different bases. So rather than dealing with these Babylonian numerals, we will focus on switching between base systems. And we might not use a base as large as 60, but we could use base 5 or base 3. And I'll talk more about that when we get there. Now let's take one of our numerals and rewrite it using the Babylonian system. So we're going to deal with 12,321, and we want to convert it into Babylonian numerals. And so to do that, we're going to have to convert this base 10 number into a base 60. When I say that this is a base 10 number, what I mean is that I can write this in expanded form. And I can represent each of these expanded numbers as a digit times a power of 10. For example, 10,000, I can write that as 1 times 10 to the 4th power. 2,000, I can write that as 2 times 10 to the 3rd power. 300, I can write that as 3 times 10 squared. 20 looks like 2 times 10 to the 1st power. And 1, as silly as it seems, we can write that as 1 times 10 to the 0 power. So we can see that we're using a base 10 place value system. And the same way that I have 10,000 plus 2,000 plus 300 plus 20 plus 1, I can write it using base 10 as 1 times 10 to the 4th plus 2 times 10 to the 3rd plus 3 times 10 squared plus 2 times 10 plus 1 times 10 to the 0. And so we're going to take our base 10 number and we need to convert it into base 60. Now we didn't need to take our base 10 number and expand it the way that I did. That was for you to see that we are using a base 10 system in our typical numeration to help us understand what to do to get a base 60 numeral. So base 60 is going to have a digit times a power of 60 plus another digit times a power of 60 that might be one less. Notice that the exponents on my 60s are decreasing just like they were on the base 10 place values. And they'll decrease for whole numbers until we get to 60 to the 0 power. What we need to do is find the digits that multiply to each of these place values. And if we started in the single place, we would end up having to rewrite everything every step of the way. So instead, we're not going to start with the smallest place value. We're going to find the largest place value that we can start with. If we're grouping by powers of 60, then maybe we need to know what those numerals look like as a full number to figure out if any of these actually fit in our number, 12,321. So let's take a look. 60 to the fourth power, we type that into our calculator. We get a really large number, 16,777,216. That's way larger than the number that we're looking for or looking at, so we know that we don't have anything in that place value. Let's look at the next smallest. 60 cubed looks like 216,000, which even that is much larger than the number we're working with, so we don't have a digit in that place value either. 60 squared is 3,600. That number is small enough to fit inside of the number that we're looking at, so we know that we can at least put a digit in that place value. To find out how many times we can use that place value, we're going to subtract that 3,600 from our number repeatedly until we've pulled all of those 60 squareds out. So we'll do 12,321 minus 3,600, which leaves us with 8,721. Now, this is totally fine to do in your calculator. If you want to do it by hand, suit yourself. We've removed one of those 60 squared groups. We need to see if we can take out more. So we take the leftover, which was 8,721, and we remove another 60 squared. That leaves us with 5,121. There's plenty there, so let's remove another 60 squared. And that leaves us 1,521. Now let's count back. We removed 60 squared a total of 1, 2, 3 times, which means we should have a 3 in that place value. Removing 60 squared 3 times did not finish the problem for us though. Notice that we still have 1,521 left over. So we need to repeat this process, but we need to look at the 60 to the first power group. We want to know how many times does 60 fit into 1,521. And we could use this repeated subtraction process if we want, or we can simply divide 1,521 divided by 60, and we can see that it fits evenly 25 times with some remainder, which means we would put a 25 in this place value. If I did this repeated subtraction process with 1,521, subtract 60 over and over and over, I would do that 25 times before I had a number that was too small to take 60 away again. We need to know what that remainder is. If I do 25 times 60, I'll see that I was able to remove 1,500. But since we were working with 1,521, we know that the remainder had to be 21. 21 is not big enough to pull 60 out of, so 21 would need to go in this last place value. So the number that we started with, the 12,321, we can rewrite that number in base 60 using 3 in the 60 squared place value, 25 in the 60 to the first place value, and 21 in the units place. Remember, 60 to the 0 is just like multiplying by 1. And if you're not comfortable with that, we can double check it. Try multiplying 3 times 60 squared plus 25 times 60 plus 21, and you'll get our original number back, 12,321. Now this is an intermediate step because we're still not in the Babylonian numerals. To do that, we would need to convert our digits, the 3, the 25, and the 21, into Babylonian numerals. So let's do that. 3 in Babylonian would be 3 of these triangles. And I'm going to try to deliberately group them together. That represents the 3 times 60 squared. And then I'll leave a little bit of a space to do the 25 times 60 to the first. 25 is going to require 2 of those sideways triangles and then 5 of the upside down triangles. And then lastly, we need 21 in the units place. That'll be 2 of the sideways and 1 of the upside down triangle. So this number that we're representing in Babylonian numerals is exactly equal to the number in our system, 12,321. The Maya numeration system is very similar to the Babylonian, except for it doesn't use place value with base 60. It uses this really strange place value with combinations of 20 and 18. Pretty strange. So it starts off in the smallest place value is 20 to the 0 power. And then it increases 20 to the first power. And then it goes 18 times 20 to the first power. So this is quite different than what we were doing before. So rather than naturally increasing 20 to the 0, 20 to the first, 20 squared, we have this weird kind of intermediate piece that is 18 times 20 to the first power. And then after that, we keep the 18, but the 20 exponent increases by 1. So then we have 18 times 20 squared, 18 times 20 cubed, and so on. So if we want to take a number in the Mayan numeral system and convert it to Hindu Arabic, what we need to do is understand how these numbers are represented within their place value. For example, if we let this number to the farthest right be the smallest place value, that's in the 20 to the 0 position. Then the next number over would be in the 20 to the first power position. Increasing up, we have 20 to the first power times 18. And then we have 20 to the second power times 18. And 20 to the third power times 18. Fourth power times 18. And then lastly, 20 to the fifth power times 18. So to convert our number, all we need to do is translate the Mayan images into our digits. This clam in the 20 to the 0 power represents 0. So we would have 0 times to the 0. And the 20 to the first power, I have 2 dots, which represent 2 singles, and then 3 horizontal bars, which is like 5, 3 times. So that would be 15 from the horizontal bars and 2 from the dots. So that would look like 15 plus 2 in the 20 to the first power. I can already tell I'm going to run out of room, so let me copy this down up at the top. Okay, moving on to our next place value, which is 18 times 20. I've got 2 horizontal bars and a single dot. The 2 horizontal bars look like 10 and a single dot is 1, so we have 10 plus 1 there. Our next place value is 18 times 20 squared. The digit that we need for that position comes from 1 horizontal bar, 4 dots. That was 4. Moving up to the next place value, that's 18 times 20 cubed. We need a digit that represents 1 horizontal bar and 1 dot, in other words 5 plus 1. Our next place value is 18 times 20 to the 4th. We have 4 dots there, so that's just a 4. And then in the last place value, 18 times 20 to the 5th, we have a single dot, which would just be like 1 times 18 times 20 to the 5th. Now at this point, we could literally type this entire long expression that we have at the top of the page into our calculator to figure out what the number looks like in our numeration system. And I would suggest that's exactly what we do, because there's not much simplifying we can do. I'm going to simplify a little bit. For example, 1 times 18 times 20 to the 5th, that's the same thing as just saying 18 times 20 to the 5th. I don't need to type in 1 times that on my calculator, it's a little silly. And then 4 times 18 to 20 to the 4th, that's not much better if we try and multiply anything, so I'll keep it the way it is. I will, however, add together any numbers that are in these parentheses by myself rather than do that on the calculator. Just realized I have a tiny typo here. In the 20 to the 0 power, remember we had a 0 digit, the clam represented 0, so it should be 0 times 20 to the 0, not just 20 to the 0. Now this is what I'll type into my calculator. And typing this into the calculator, whoops, I get 70,053,100. And it's very possible to make mistakes typing this into your calculator, so be very diligent. Check your work a couple of times when you're trying these. We're looking at really large numbers here and a lot of formatting mistakes that could happen, especially with these exponents and multiplying. So to take a number in the Mayan numeration system, we first rewrite it in base, well, it's kind of base 20, but this 18 that starts right here throws it off. It's not truly base 20. But we write it out in expanded form like we did up here at the top of the screen, and then from there we just multiply. Now doing the reverse, taking our number and rewriting it in the Mayan system, quite different. I'm going to reuse what we have at the top of the screen and just take out the digits that are in each place value so that we can fill them in to represent this new number. Now some of these place values are going to be way too big for the number that we're working with, 12,321. So the first thing that we want to do is find out what's the largest place value in this numeration system, in this weird base 20 with an 18 in there. It's the largest place value that will fit inside of our number. So let's try with 18 times 20 to the 5th. That is way too big. 18 times 20 to the 5th looks like 57,600,000. So we know that that place value is not necessary for the number that we are working with. So we move down a notch. 18 times 20 to the 4th. That is also too big, 2,880,000. Move down to the next one, 18 times 20 to the 3rd. That is 144,000, still too big. 144,000 is much larger than 12,000. So we move down to the next one, 18 times 20 squared. That's 7,200. Now that place value is the first one that is small enough to fit in the number we're working with. And we want to know how many times it fits. So if we take our 12,321, divide it by the 7,200, we can see that it fits in once with some remainder. So what that means is that 12,321 is 7,200 plus some remainder. And we can find out what that is simply by subtracting 7,200 from our original number to find out that that is 5,121. So that remainder was just too small to take another 7,200 out, which means we can only put a 1 in this place value. We only have enough to fit one of those into our number. And then from there we work with our remainder. Moving down to the next place value, we're looking at 18 times 20, which is 360. I want to know how many times can we take 360 out of our number. So I'll divide 5,121 divided by 360. It fits in 14 times with some remainder. So we can do 5,121 is equal to 14 times 360 plus some remainder. I could do the subtraction there, 5,121 minus the 14 times 360. I have an 81 remainder. Now, because we were able to remove 360 14 times, I'll put a 14 in that place value. And then moving down 20 to the first power, I'm looking at 81. So 81, I know that I can pull 20 out 4 times, because 20 times 4 is 80. And then in our last place value, we would only have 1 left, so I would put a 1 here. Now that we have this number written in the correct base system, we can convert our digits into symbols like the Mayans used. And we'll put those in order. So we have 1 in the largest place value, which would look like a single dot. We have 14 in the next place value. We would need 4 dots for that. And then we would need 2 horizontal bars. The next place value, we have a 4, so we'd have 4 dots for that. And then in the very last place value, we just have a 1. Oh, I put that in the wrong number. There we go. So that number, those dots and bars, is equivalent to 12,321. Next, we'll talk about the Roman numeration system. You've probably used Roman numerals before, so I'm not going to go too deep into how to do these. Basically, it's very similar to the Egyptian numeration system, but instead of drawing pictures, you're using these Roman numerals that look like letters, like I, V, X, L, C, D, and M. And unlike the Egyptian system, these aren't perfect powers of 10. We have groups of 5s and groups of 10. 5, 10, 50, 100, 500, and then 1,000. And so we're already working with different images rather than the pictures. Now we're working with letters, and also each letter represents very different values than the Egyptian system. And then there's another thing that's pretty neat about the Roman numeration system, and it's how you can create numbers by pairing up a number with a smaller numeral. For example, we can see that the numeral I, which represents 1, is smaller than the numeral V, which represents 5. And if we start with big to small, then we're following the place value correctly. So if I did like V and then 1, that would say 5 with another 1. That would look like 6. But if I do it reverse, small before big, then it's like a subtraction. If I did 1 and then V, that would say 1 less than 5. That would be 4. So using the same digits, depending on the way that we position them, they can represent different numbers. I'm going to skip the translation between these different systems because I'm hoping that Roman numerals are familiar enough with us and that we can read through the example in the book on our own.